I'm just going to introduce myself because there's not much to it. I'm Alta de Waal from the University. I almost said the University of the Free State because that's where I was born and bred. But I'm now with the University of Pretoria, and I'm also affiliated with the Centre for Artificial Intelligence Research, which is basically a consortium of many universities in South Africa that focuses on AI. So I'm going to talk today about how to establish semantic similarity. Specifically in text, and I know I said short text, but then I realized usually you want to do it on short text anyway. So it's, you always want to do semantic similarity on phrases. So by definition, it's almost short text. And I can make this a very technical and intimidating presentation, as I'm sure all of us can do, but I decided to do it more in a tutorial kind of way, so that you can walk away and hopefully try to do it yourself. So I'm going to explain the steps and the ingredients that you need in order to do semantic similarity analysis. So if we think of different kinds of data that we want to analyze, then image, sound, and text comes to mind. Now, we as humans can interpret an image, we can interpret sound, and we can interpret natural text in a natural language. But a computer can't do that. And I think that's also what Jacques referred to as AI is actually done. We need to take image, sound, and text and make it understandable to a computer. So we need to transform what we understand as humans to numbers or vectors that a computer can understand. And I'm going to specifically focus on unstructured text or unstructured data for that matter, which means it's unsupervised learning. So the challenges that we have with unstructured text is that we have no metadata available. So we don't have labels associated, or at least it's optional. We might have metadata, but it's not to say that it is there or that you want to use it. So the observations are not labeled. So we can't do classification. And the veracity and uncertainty associated with unstructured text is really high. You don't know what you deal with because usually you don't know if one part of your corpus or images differ completely in genre from another part. So there's a lot of veracity that's associated with it. And it's usually very high dimensional. And I will explain to you what high dimensionality means in terms of text data. But with all challenges comes opportunities. And the thing with unstructured text is it's abundant. We've got loads and loads of unstructured text. So we've got much larger volumes. And to label data is really expensive. Humans need to do that. The other thing is it's current. That's also usually the problem with labeled data. By the time you've labeled your data, it's old. And we know that there are underlying semantic patterns that exist. We know that there's some way that the data was generated that we can in some way find. And that is where the manifest, it's not a manifest, sorry, it's the manifold hypothesis holds true. I don't know why I said manifest. So I was probably reading some document or proposal that I had to do. The manifold hypothesis holds true, and what does it mean? It means that high-dimensional spaces, such as speech or text, tend to lie in the vicinity of underlying low-dimensional spaces, which we call manifolds. And that is basically also why we have deep learning. Because if you think of all the layers that we get in deep learning, those are the manifolds that we learn in the data. It's the underlying patterns. And if we believe this hypothesis, then we know that somewhere we must get something that is a lower dimension that we can actually work with. So if we think about text analytics, what are meaningful analyses that we can do with text? First of all, we can get descriptive statistics. We can count the number of words. We can get the vocabulary. We can see. We can look at the frequency. So your most basic descriptive statistics already gives you a lot of information about your corpus. Then we can transform our words to understand the content and context of our text. And that is also what I will show you. There's a saying that says content is king, but context is queen. So there's one way to know what's your content, but what if you have 1 million tweets? How on earth will you know what that corpus is about if you don't understand the context? And once you have that transformation that makes you understand the context of your set of tweets or documents, then you can start to understand how they are similar to each other. So those are the 3 phases of meaningful text analytics. And one of the things, and specifically with unstructured text, the moment you have supervised learning and you do classification, then you do things like sentiment analysis or spam classification, email spam classification, because then your data is labeled. Then it's a completely different ballgame. But when you have unstructured text, then this is typically what you want to do when you do text analytics. So I've come up with, not me, myself, but I made this chart for you, and this is what we're going to go through in this presentation. So there are 3 phases to what we want to do when we want to understand the semantic similarity. First, we need to do pre-processing of our data, and that is where NLP comes in. Because we need to tokenize our data. We need to transform it to vectors that the computer can understand. So the output of this first part of the process is documents represented as a stream of vectors. And it's also called vector space modeling. So once we have our documents represented as a stream of vectors, then we can look at transformations. And this is where we want to find the hidden structure of the documents. We want to understand the relationship between the words in our corpus. And we want a compact document representation. So we want to go from a high-dimensional space of document representation to a compact space of document representation, like clustering or dimensionality reduction. And then once we have that transformed vector space, then we can look at similarity queries. So this is where we get a new document, an unseen document, which we want to query. That can be like when you enter a search term in Google. So you convert that query document to the transformed vector space, and then you index the query document, and you calculate the distance between the query document and your reference corpus. So the output there is a distance measure. So I'm going to take you through this process. So if we look at what do we need to do when we read text data, first of all, we need to clean the data. Decoding is your worst enemy always with text data. You will always get an encoding issue. So you need to just work through decoding. Obviously, we remove all HTML markup. It doesn't have any semantic information that we are interested in. We typically split on the white space. So a word is the basic unit that we work with. We remove special characters, numbers, and stop words. And you can also have corpus-specific stop words. So that is where it's in your corpus. Say you work with a corpus about health. Or in the medical field, then maybe you don't want the word health in your corpus. It's almost like a stop word because it occurs too often. So what are stop words? They are words like is, there, and, etc. So semantically, they don't have any value, so you want to remove them. You will also see later on that there's other reasons also why you want to remove stop words. And then words that occur, say, not less than once, but less or equal than once or twice, or even up to 10 times, depending on how large your corpus is. Because statistically, they don't add value. So there are two reasons why you want to remove words. The one is if they don't add any semantic value, and the other one is if they don't add any statistical value for your model. So just some terminology. So what we said is the basic unit that we work with is a word. So a word is a feature. And a grouping of words we call a document, but it can be a tweet, it can be a review, it can be a news article. So any grouping of words. And then the grouping of documents is called a corpus. So the descriptive stats that we get the total number of words and documents, and then we also get the vocabulary. And the vocabulary is the list of unique words in your corpus. And typically if you work with a corpus of, say, around 10,000 documents, after pre-processing, you typically have between 15,000 and 20,000 words in your vocabulary. So that means your dimension size is 20,000. You've got 20,000 features. And any statistician gets a nervous twitch when we go beyond 3, the dimensionality of 3. So you can just imagine it's chaos. And that's why we want to reduce it. Yes?
The question, when you remove it, especially like it's a punctuation, I can believe a lot of instances it is quite essential for the meaning of the relationship. So is it after you find that statistically it's not that meaningful? Or, because in a lot of instances it actually makes a massive difference in the relationship between the words and how they appear. So isn't a way of actually adding them in as some sort of...
The thing is, you will see later on, we work with a bag of words representation. So you remove the structure of the sentence. So you don't have part of speech tagging or... So you just count the words. So in that case... Yeah, so then the use for punctuation falls away. What we've done is we've once done topic modeling on tweets where we kept the emoticons. So, but then the emoticon was like a word. So we treated it as a unit. So you can choose, like for example, I've once worked in a forensic application with emails and faxes. It was in the old days of faxes. So there we kept the fax numbers but that was also more for metadata that we kept that. So you can decide, and of course you can do this with images as well, and then your pixels are your basic unit. So anything that you can, any discrete data that you can count, you can choose to add it to your vocabulary. But you always want your vocabulary as small as possible. Most of the time, you would rather remove words. So, for example, what you can also do, obviously, part of pre-processing is also if you have a spell checker. If you know you have English, then if you can do text normalization. So there are a few NLP techniques that you can use in order to reduce your vocabulary. What we also sometimes do is we do part of speech tagging, and then we decide we're only using the verbs, or we're only using the nouns. Or we do some chunking where we have a pattern like an adjective and a noun, because you want something like white house, pink feet. So there are some chunking phrases that you would like to keep as a unit rather than one word. Okay, so here we get to the bag of words vectorization. So this is how we translate from natural language to a vector. So bag of words is a count representation of natural text. So we first get the vocabulary, and then we count the number of times each word appears in the document. And the result is a document by a word matrix. So in this case, you can see word 1 occurred 11 times in document 1. And this is a very sparse matrix, because most of, if that's a dimension of, say, 5,000 by 16,000, then you can, and your average document length is 20 words, then you can imagine that you have real sparsity going on there, especially when you work with short text. Okay, so and there's just an example. It's really very basic. So there's Julie loves me more than Linda loves me, and Jane likes me more than Julie loves me. So in this case, I didn't remove any stop words. And this is what this simple bag of words matrix looks like. And coincidentally, they both add up to 8 words. Okay, so now we get to transformation. So now we are in phase 2 of the process. So we've done bag of words representation. So we've got a vector representation that we can feed to our computer, and the model will understand it. So the objectives of the transformation that we want to do is we want to bring out the hidden structure in the corpus and discover the relationship between words. I always think of these models as little hooks that hook words as they co-occur in documents, because it's all about counting. And all about counting co-occurrences of words in documents. That's basically what these algorithms are all about. So we want to use these relationships to describe the documents in a more semantic way. And what does semantic mean? And that's an ironic question, because semantic means meaning. It's about meaning. And then, like I said before, mathematically, we want to make the document representation more compact. So what are the types of transformation? The most basic one is, I suppose, principal component analysis, although you shouldn't actually do PCA on this discrete account data, but you get exponential family PCA, which basically leads you to topic models like latent Dirichlet allocation. I think the most basic one is term frequency, inverse document frequency, and I'll get to that. Then we have topic models that I also explained to you, and then when we move to the deep learning domain, then we get word and sentence embeddings, and those are algorithms like word to vec, or sentence to vec, GLAV, fast text, etc. There are many of those. So this is just TF-IDF. Basically, you get the term frequency across the documents, and then you get the inverse document frequency, In this case, N is the total number of documents, and the denominator counts how many documents contain the term J. And then you just multiply those two, and you just add it up. And that is TF-IDF. So let's get to topic models, because that is basically what I want to talk about a little bit more. So topic models are algorithms that aim to discover and to annotate large archives of documents. So again, say you have a corpus of 1 million tweets. How on earth would you know what is going on in that corpus? There's no way that you can get a good idea of what that corpus is about. And topic models aim to annotate and cluster those large corpora. So there are statistical methods that analyze the words to discover the themes that run through them, and I'll show you an example of that. To understand how the themes are connected to each other, and then they can also you also get topic models that can show you how they change over time. So if you take, say, a theme like physics, then physics 50 years ago has got different words than physics now, but it's still physics. So you can look at the evolution of topics. So they don't require any prior labeling, meaning that they are completely unsupervised. It's only the discovering of topics. And they enable us to organize and summarize these archives of documents in a way and on a scale that is completely impossible for humans to do. Topic models are very popular in the domain of digital humanities, where they look at large archives of historical documents and trying to understand what those archives are about. So, and then when we move to probabilistic topic models, then they follow the principle of generative models. So they make an assumption about how the document was generated. So they discover the patterns of word use and connect documents that exhibit similar patterns. So you make an assumption about how a document was generated, and if you make that assumption, and if you can build a generative model, then you can discover the latent topics. And I'll show you the graphical model of a topic model just now. And basically, if you go into the mathematics of topic models, then it's really where clustering and dimensionality reduction meet. So a topic model possesses characteristics of both clustering and dimensionality reduction. So a corpus is now represented as a lower dimensional form by a set of topics. So instead of having a vocabulary of, say, 16,000 or 20,000 words, you can now represent that corpus with, say, 500 or 100 topics. So you lower your dimensionality in an extreme way. So, and for me, the main advantage of these topic models is that they produce labels. So it means that not only do you cluster, but you also have a way to explore your corpus, which I will show you just now. So for me, the main benefit is that they are designed to not only provide data compression, which we are interested in from a machine learning perspective, but they also produce topics which are interpretable. So this is the graphical model of a topic model. So that plate there runs across your documents. So you've got M documents, and N is the number of words that you have in a document. And your observable variable is your words, and there is your topic. That's your latent variable. So what you say is, for each document, and for each word in each document, you choose a topic. And that alpha and beta are your hyperparameters, and that theta gives you the topic by document distribution, so that does the clustering for you. And beta gives you the word by topic distribution, that does the compression for you, or the dimensionality reduction. And theta has got predictive abilities. So that means if you get an unseen document, you can predict in which topic it will fall, so you can predict. And the word by topic gives you exploratory abilities. It tells you what the topic is about. And those are examples of topics. So you don't get a label. You don't get like topic A is about finance. But luckily we as humans are very good to interpret the top 10. So basically what you do is you have this word by topic distribution, and if you sort each topic vector from the highest probability to the lowest probability, then the top words gives you a good description of what the topic is about. And I think all of you will agree with me that topic A has something to do with finance and maybe even Black Friday and markets, financial markets, and topic B has to do with maybe the Gulf War in Saudi Arabia, etc. And this also shows you the benefit that you have if you can combine words like New York. Because in that case, New and York takes up two very valuable spaces in your top 10 description. So, and there you have Saudi Arabia. So using NLP techniques, if you can get bigrams, then you get much more meaningful words or concepts in your top 10 words. And that really helps, especially when you work with a corpus that you have no prior knowledge about. So when I did my PhD, I did my case study on a digital forensics case study. And that was such a typical case where you confiscate, say, 10 computers, and now you need to analyze the natural text on those computers. So you've got no idea of what is going on. And then NLP becomes very valuable as a pre-processing technique. Okay, and you can visualize your clustering in many creative ways. And again, trust the digital humanities people to come up with these very organic representations. I've got no idea what it means, but it's so beautiful. And the reason why I also show you this is because for me, those latent semantic structures are very organic. You know, it's abstract. We don't know what it is. You know, it's almost like this little alien, you know, that's, you see always in alien movies where the alien starts to grow. It feels, it's like that. It's a very organic, uncertain thing that grows. So for me, thinking of, and it can be anything. You've got your transformation of choice, whether it's a word embedding, whether it's a TF-IDF. It's something that you can't touch. It's latent. And that's another nice, beautiful one. And this was made in a software called Gephi or Gephi, G-E-P-H-I. It's really a very nice software package if you want to do pretty visualizations. So, where are we now? What have we done so far? So here we have our text. And then we have our vector representation, our bag of words. And now we have our manifold representation. So we've managed to find that hidden, latent structure that we can actually work with, that's manageable to work with. So what do we want to do now? We want to look at semantic similarity. So first of all, what are the ingredients? We need a query document. So think of it as when you Google something and you type in what you are searching for, that is a query. And then in the background, there's this context documents or reference documents that you want to bounce your query off against. And you want to understand how closely or how similar is your query document to your context documents. So you also need your semantic structure. Remember, your semantic structure is your little amoeba there. Your manifolds, the thing that you can't see. And then you need the distance measure. So those are the 4 things that you need. The steps is, first you need to vectorize your query and your context documents. So you need to get them all in this structure. So you need to vectorize them. And then you need to index your query and your context documents. And then finally you calculate the distance between the query and the context documents. So there's your query document and there's your context document. Now, documents. Most of the time, you get this structure from your context documents, but that is not a given. So what many people do with similarity indexing is they take a large corpus like Wikipedia and they train, especially with word embeddings, they train this latent structure on that large corpus, and then you just index your context documents and your query documents against this. And that is fine, but sometimes you work in a very, very specific genre. Like, say, for example, the example that I will show now, wine reviews or beer reviews or tweets. And then it's very difficult. Then you can't really use something like Wikipedia as to learn your latent structure because it's just completely different in genre. So you index against the semantic space and then you get the semantic similarity between the query document and your context documents. So where do you get that? If you look at the topic model, then beta gives you the semantic structure and theta gives you the indexing, because this is the clustering and that is the dimensionality reduction. So that is where you get the information. This is just an example on topic models. So when you want to do similarity, you can use any distance measure, like cosine similarity, for example. So basically, or you can, it's just the inner product that you get between the 2 vectors, because remember, you've vectorized all your documents. So you just get the cosine similarity between the vectors. And if you've got no similarity, then your measure is 0. And if it's exactly the same document, then your measure will be 1. Now, the catch is, cosine similarity doesn't work on count data. And there are good reasons for that. The one is stop words, because stop words occur very frequently. And it messes up your similarity. So, because it doesn't give you semantic information. And then you get another thing that they call burstiness. And that is a very interesting concept which says that if you tend to use a word, if you start to use a word like, say, hence, or I don't know what, if you write your thesis, or you write your dissertation. I see that when I examine dissertations. You start to see people start to use words in a paragraph more often. And that is called burstiness. And that also messes up your cosine similarity. So this is a mathematical reason why you need to do dimensionality reduction. You can't do cosine similarity just on count data. So the solution is to perform your similarity on your semantic structure or your transformation. And also, what is also important is if you do a probabilistic transformation like topic modeling, then it's not a good idea to use cosine similarity. Rather use something like the Hillinger distance or the Mahalanobis, distance. I can't say Mahalanobis. Now I can. Okay, so just to summarize, these are the steps. First we do pre-processing, and there it helps to have some NLP experience, and it helps to work in English. Luckily, in South Africa, we've got great resources for all 11 African languages. The Northwest University has got a resource management agency that has got speech and text data in all 11 official languages. So if you ever want to work in any other language, they even have spell checkers, I think. So if you want to work in any other language, just Google Northwest University Resource Management Agency. It's really a fantastic resource that many people worked very hard on, and that the Department of Arts and Culture sponsored for many years to build up, to have these human language technology resources. So it's something that we can be very proud of. I get very passionate about that. And then you do your transformations. So I'm more of a probabilistic type of person. But I think in many cases word-to-vec or GLOVE or fast text works better, especially when you have a lot of data. Then those will work well, and if you've got nice big computers. But if you have a small corpus, then I would fall back on the probabilistic models, because then it can handle the uncertainty better. And then you do your similarity queries, and that is a process. So finally, let's quickly look at an example. So I thought while we are in the Cape, let's look at wine reviews. Now I've got an extremely small corpus, only 9 reviews. They are all, so the first one, the ripe aromas of fig, blackberry and cassis are softened and sweetened by a slathering of oaky chocolate and vanilla. So, don't you think we should, for the deep learning in Indaba, do a competition on wine reviews? There's a very nice data set on Kaggle. Anyway, so this is my corpus, and in this case, I'm going to train my semantic structure on this small corpus. So it's actually not going to make much sense, but I just want to show you, I just want to take you through the process. So this is what was left after I've done pre-processing. So in this case, I've removed some stop words. You can see there's R, E's, and on. I haven't removed all of them, otherwise I won't have anything left. And I've also removed words that only occur once in the corpus. So you can see how quickly you run into sparsity when you have short text. So this is all that you've got left. This looks a little bit sad. So I've done a topic model. I've done latent semantic indexing in this case. And I've only trained 2 topics. So I've reduced my dimensionality from, I don't know, I can't remember what, I think there are about 16, my vocabulary is 16, and I've reduced it to 2. And you can see topic 1, those are the top 5 words. So it's aroma is second highest, and then ripe, and then fruits, and for topic 2, balanced is the top word. So those are that latent structure that came out of this corpus. And then I have a query document. Yes?
Why 2 topics?
Oh, that's a good question. So that is falls into the same category as why 5 layers in your neural network, or why, you know, it's something that there are ways to test which ones work the best, but the problem is because you do unsupervised learning, you don't have very good metrics. So there are ways to measure the stability of your topics, etc. And then you can also go the non-parametric route, where you do something like a Drichley process to learn the number of topics. But obviously with such a small data set, it won't make sense. So you play around until you find something that works. So yes. Yeah.
In that case, if you tested like 5, 4, 3, 2, 1, and then you found like 3, it makes sense to me. And so that's how you justify it.
Yeah.
It just makes sense.
There are ways. So, like I said, you can do topics. There are ways to measure topic stability, and you get metrics like the one is the UMass metrics, but most of them has to do with stability. So, also what you do is, because you have a stochastic process where you have different initializations, you will run it, say, 10 times, and then you look at stability. The classical way to measure it is perplexity. But these days, many people believe that perplexity is not a very good representation of the quality of your topics. So it is a little bit of a trial and error, because many times you will run a topic model and then you will get meaningless topics or background topics. And then you have to go back, do more pre-processing. So yeah, as with any unsupervised technique, you know, it is a little bit of a trial and error. Okay, so there is my query document. So this is a new review. My model hasn't seen this review. This fresh and lively medium-bodied wine is beautifully balanced with ripe flavors and a tangy acidity. And then I index it. And there is the index against topic 0 and there against topic 1. So you can see it's got a higher probability for topic 0. So to which review is the query most similar to? So there I have all my distances, and it's most similar to review 8. And review 8 is the last one. So you can imagine that with this small data set, it doesn't really make sense, but this is just to show you, just to take you through the whole process. And then lastly, I just want to give you some resources. Rare Technologies is the company owned by the person whose name I can't pronounce, who wrote the Python package Gensum. And their blog is really fantastic. So they've got so many tutorials on their blog, anything about word2vec, etc. And then Gensum itself, he says it's topic models for humans. I don't know what other species wants to do topic models, but anyway. And then Fearsome Engine. I don't know if you remember with the Deep Learning Indaba, Precalc Consulting sponsored the top prize. Now, Fearsome Engine is a product from Precalc Consulting, proudly South African or African. They do chatbots and services like that for rural communities and social good in South Africa. And then many of you should know Kaggle, when it comes to data sets. And I rely a lot on these resources to assist me when I do similarity indexing. Thank you very much.
Thank you, Dr. De Waal. We've got 10 more minutes for questions.
The features you started off with is simple word count. And one of the side effects was that cosine similarity is not a good measure there. Aren't there more intelligent ways to choose those features, to some sort of information measure that says this word is more significant than other words?
So that is basically what TF-IDF is. So it's a statistical measure. So if you look at the TF-IDF, then that term frequency, inverse document frequency, basically gives you that significance of the words. Yes, so that is the most basic thing that you can do, but that doesn't do any dimensionality reduction. So you can do two things again. Either you remove words semantically or using NLP, or you remove them statistically. Yeah, so it's always one of those two methods that you use.
Regarding you mentioned that in your PhD you're working with data that you obviously aren't familiar with, and then you visualize it and you see that. What process did you go about, with certainty interpreting what's happening in the data if it's something you can't back up? Like if you collected the interviews or you collected the data, you pretty much know what the topics are saying, so you know, okay, I need to pre-process because I'm not getting the right thing. But that sort of bias where you just don't know what you were meant to be getting, so you don't know what the topics mean, or, so how did you mitigate that?
Okay, so with the forensic investigation, we work together with a client. Which in that case is the police or the special investigators. So we actually picked up surnames, for example. Or like when we only did topic modeling on the verbs, we got words like said, accused. So it is all about interpretation at the end. And sometimes you do get junk, but at least it's a lower dimension as the original junk. Yes. So it's something that you can work with. But like I said, it's a lot of trial and error. Usually when you do topic modeling, you go back and you clean your corpus again. And yeah, so it's really a process to get to a point where you have a clean vocabulary.
Just from a tools background, I haven't been able to find with Jensen a way to do LDA with background topic as well.
Are you asking or?
I'm asking if you know of users that can do that.
I know. I actually saw on Twitter that Jensen asked if someone wants to do background topic modeling in Jensen. So now I don't know. Yeah. Okay. Thanks.
At what point do you bring in data outside of the corpus? So, for example, knowing that words are synonyms or antonyms.
Okay, so topic modeling does that for you. It's able to pick up synonyms and antonyms, and also like the word bank. It can put it in a topic about financial banking and also about, say, river banking. So it does it automatically because it's about the word associations. Then you get other type of topic models like author topic models where you can bring in, say, authors if you have that information. So there's and you can also do supervised LDA, so you have reviews and you want to look at the topics for all the one-star reviews. So there's ways to bring in metadata like that. Yes.
Would you be able to use this on your own data where a lot of the words are merged together?
Yeah, usually I just throw out URLs because semantically they don't have meaning. Yeah, they don't.
Your data is predominantly URLs with slashes in between, like your first domain and
Then you must. So what typically happens sometimes when you do splitting in string splitting in Python, for example, then you can choose to split on the punctuation, and then you will be able to get that middle part. Yeah. So that's if you have some rules like that or regular expressions, then you can do manipulations like that to get that middle part.
Right, thank you. We all can see that.